From here to the stars, I am your host, Stephen Euin Cobb. Our guest today is Dr. Pete Worden. He is chairman of the Breakthrough Prize Foundation, executive director of the Breakthrough Initiatives, and former director of NASA Ames Research Center. Our guest today is Dr. Pete Worden, chairman of the Breakthrough Prize Foundation, executive director of the Breakthrough Initiatives, and former director of NASA Ames Research Center. He is a recognized expert on space and science issues and has been a leader in building partnerships between governments and the private sector internationally. He is also a sponsor of the IRG's 8th Interstellar Symposium, which will be held next summer on July 10 to 13, 2023 in Montreal, Canada. Thank you, Doctor, for taking the time for this interview.
Well, thank you, Steve. Honored and pleased to be here to talk to a group of fellow interstellar enthusiasts.
Okay. A few years ago, on December 15, I interviewed Dr. Philip Lubin, who introduced me to the idea of sending thousands of tiny 1-gram spacecraft to other star systems. Very exciting stuff. If you would, describe for those who may not be familiar with it, the ideas that compose Breakthrough Starshot.
Breakthrough Starshot is probably, to me, our most exciting effort. We're part of the Breakthrough Prize Foundation and Breakthrough Initiatives. Our primary focus is finding life in the universe and understanding life in the universe. But there are three parts of it. One is, can we find any life elsewhere, evidence of it? And two is any of it intelligent enough to communicate with us, or maybe it's intelligent enough not to communicate with us. And the third one is an old interest of mine is, can we actually send probes interstellar distances? I was recruited by Yuri Milner, who was the founder of the Breakthrough Prize Foundation, in about 10 years ago. I was still the director at NASA Ames, to come and lead his privately funded effort to look at all three of these topics. In the 1st of April 2015, I left NASA, and the first thing we did was we prepared for a announcement of a Breakthrough Listen, which was a SETI effort that was announced on July 20th, 2015, at the Royal Society in London. Stephen Hawking was our science advisor. He was there. But we really wanted to do more than that. About 9-10 months later, we announced Breakthrough Listen, which was our search for life in the universe. But then on April 12th, the anniversary of Yuri Gagarin's historic flight, we announced Breakthrough Starshot. And our objective was to figure out if we could send probes to the nearest stars in our lifetimes. And well, maybe not my lifetime, I'm 73, but possibly, and do a mission that was basically a 20-year mission to fly by nearby stars, particularly the Alpha Centauri system. We announced that program at the New World Trade Center on April 12, 2016. It was Stephen Hawking's last trip to the United States. As everyone knows, he passed away a few years ago. But to me, it was really the highlight of our program. At that time, though, we really didn't know how we were going to get there. But a few months before, I had met Professor Lubin, and we did a sort of major study that Professor Avi Loeb at Harvard ran for us, and figured out that Phil Lubin's idea of taking a very powerful laser and driving a light sail, and in our case, the light sail would be 5 or 10 meters in diameter, with light pressure, and attaching to that sail a what we call a nanocraft. It would be a Graham-class spacecraft, and the idea is, if you could build a big enough laser, and you could place these nanocraft in orbit, and in our case, probably would have them on a mothership that would be probably the size of a communications satellite that would be in a highly elliptical orbit with its apogee pointed towards our target, which is notionally the Alpha Centauri system. That it looked like that we could make this work. Now there's formidable challenges. We want to do this affordably, and now of course affordably for billionaires is different than affordably for you and I. But we felt that something that would be comparable to maybe the James Webb Space Telescope, so roughly 10 billion euros or dollars or pounds or whatever your favorite currency is. As long as it's not ruples, and we found that the first challenge is can you build the laser device, the photon engine as we call it. The second big challenge is can you build material that can take this? It's 10 or 100 gigawatts of power or more, and you're trying to focus this on something that's 5 or 10 meters across. The energy density is really incredible. Can we build a material that could reflect virtually all that light, and what it didn't reflect, transmit without absorbing it? So that was a big challenge. The third one is can we actually communicate signal back from the nearest star system? And to remind everybody, that's the Alpha Centauri system at 4.3 light years, so roughly 300,000 times further away than the sun. So we started Breakthrough Starshot. Our sponsor, Yuri Milner, committed ultimately 100 million, assuming that we can solve these problems. We have just now completed phase one. We probably had about $10 million worth of contracts around the world to answer these three questions. In the next few months, we're going to be talking to our sponsor and our advisors. And I think that, at least from my perspective, the answer is yes, this could be done. That we think that we could build a photon engine of the right power, and this is a big photon engine. It's kilometers in scale. Probably the most amazing set of breakthroughs is one is that the Australian National University showed that you could phase the signal. You have to in order to get this to focus on the light sail, which would initially be about 60,000 kilometers out, and then accelerated over a few tens of minutes to 0.2 C, 60,000 kilometers a second. We need to be able to phase the signal across kilometers. Australian National University did a research program and showed us that yes, indeed, this can be done. And actually, Professor Lubin has got another contract with us, and he also showed that it could be done at UC Santa Barbara. The big question is, can we build the laser array cheap enough? And there are a set of technologies being developed. One is integrated diodes, laser diodes. Another one is actually photonics, where this is a chip that produces a laser signal that can be phased. You can build something that looks a lot like a solar panel, but instead of receiving power and translating it to energy, this you put power in and you translate it to photons that are in phase. One of those programs is called VEXELS, and a few others are being done. So we think that can be affordably produced in kilometer scales. And as we know today, we have kilometer scale solar arrays that are affordable. So this is sort of a feasibility effort. The third one is, of course, can we build a light sail that can take this? And Professor Harry Atwater at Caltech has led our effort on that, and it appears that there are materials. One of them is silicon hydride, and that does seem to have the right characteristics. Today we can build these in a few millimeter scales, and we have to build them in 10-meter scales. But as a scientist, I'm fond of saying that's just an engineering problem. So that's those are the two ones. But I think the biggest challenge is how do we get the signal back from Alpha Centauri? And you've got the entire spacecraft that's a few grams. So one of the big questions is how do we focus the laser light? Can we power a laser, at that distance and get the signal back? And can we receive it? And we have a third effort that Professor Phil Mauskopf at Arizona State University has led for us. And it appears the answer is yes. Basically, what we do is that the light sail itself becomes an integrated sort of electronic element, and embedded in it is everything the spacecraft needs, but also transmitters, laser photon transmitters, that it can be electronically focused, so that you take a few square meters of this and actually focus a laser beam back on the Earth. The power is a challenge, but we think a combination of a maybe very small nuclear radiation elements that produce energy. Possibly we pull energy off the sail itself as it goes through interstellar space. It turns out one side is heated by the gas that's going at 20% the speed of light relative to the other. We can get power off that. And furthermore, if we're in the Alpha Centauri system, we can get starlight and convert it. So we're looking at a combination of those. The big problem is that beam, even from a meter or two of the light sail, is still tens of kilometers or tens of millions of kilometers in diameter when it reaches us. So there's not a lot of photons. So we've looked at, can we build a receiver, and the receiver has to be a good fraction of a square kilometer. So it's a telescope. And now today, the biggest telescopes we can build are maybe 30, 40 meters in diameter, and those cost billions. But there's some amazing breakthroughs that are being made in building telescopes that are really cheap. There's two groups in particular. One is Professor Jeff Kuhn at the University of Hawaii, and another one is Professor Roger Angel at the University of Arizona, that have developed capabilities that look like we could build a half square kilometer optical element for, again, of order of $1 billion or $2 billion. So those all look very promising. Hopefully our sponsor will agree to go forward with this program. There are other sponsors funding some of these other parts of these efforts. So we're beginning to kind of see a group of people coming together. And probably the biggest question is there anything in the Alpha Centauri system interesting? And now when we started this program, we didn't know of any planets in that system. In fact, there were some people that said, well, the two major stars, which are solar type stars, orbit each other around 80 years. And, a lot of astronomers said, well, their model said you couldn't form planets in these binary star systems. Now, fortunately, the universe hasn't heard those analyses. The Kepler mission, which was one of my missions at NASA Ames, has found binaries that have planets. But there's a couple interesting things. First of all, the Alpha Centauri system is a triple system. The third star is a small red dwarf, which orbits very distant from the other two. And after we made our announcement of all of our programs, the European Southern Observatory announced that they had discovered, through indirect means, an Earth-sized planet orbiting Proxima Centauri, the red dwarf, in the habitable zone. Now, habitable zone is pretty close to the star because it's only about 10,000th the solar luminosity. Since then, there are two other planets been found in that system. There's a second one that's also in the habitable zone, and then a bigger one that's not. But one of the things we've always been interested in is, what about the two primary stars? They're solar type stars. And if you do a calculation, you say, well, if a planet was orbiting around 1 astronomical unit from them, about where the Earth is from the sun, it should be stable orbit for billions of years. So there's no reason you couldn't have a planet there. So we mounted a program with the European Southern Observatory to do a infrared coronagraph. This is a device that blocks the starlight so you can see a really faint object next to it. We picked 10 microns because at that wavelength, something the size of the Earth radiates its maximum amount of energy in the infrared, and the contrast between it and the star is just a geometrical ratio. It's like 1 part in 10 to the 6th. Whereas if you go in the visible region of the spectrum, it's 1 part in 10 to the 9th, because the planet's just shining by reflected starlight. We had about 100 hours of time, and we had a tentative detection of a giant planet orbiting in the habitable zone of Alpha Centauri A. And that was kind of exciting. I mean, it was a 3 sigma result, meaning that it's probably real, but you can't prove it. The first thing that was interesting is in the movie Avatar, there's a giant planet orbiting in the habitable zone of Alpha Centauri A, which has moons that are not only habitable but inhabited. The giant planet is called Polyphemus. The thing that we tentatively found looks like it's a giant planet. So our sponsor knew James Cameron pretty well and got in touch with him, and he was very excited about it. He actually did a video discussion of the physics and everything of Avatar, that we might have discovered, that science fiction preceded science fact. It was also interesting that his terrestrial starships that go there, the outbound journey is powered by lasers, just laser light rail. And so we were pleased to see that maybe that we had the right answer. At the other end, it's stopped by a fusion propulsion system, and I'm actually quite excited that we're seeing fusion propulsion coming along. We have another program that we've just kicked off. It's a small satellite that's being built for us by the University of Sydney in Australia that we think will launch in probably a year and a half from now. It's called an astrometric mission. So what it's trying to do is look at Alpha Centauri A and B referenced very precisely to each other, a few millionths of an arc second. So if there's a planet orbiting one of the stars, this distance will wobble with time. You'll get a modulation. So we think that we certainly, if the planet we found is real, we'll be able to detect it with that, or potentially other planets in that system. There are other programs that we're looking at in the longer term that might involve space-based systems that could directly image these planets. But it's very exciting, and I'm hopeful that we can begin building prototypes of some of these within a decade, and the full system within about a few decades. But hopefully these are the first steps for us becoming interstellar species.
Okay. Since the idea is to send many probes to one star system, would they scatter to pass the star on all sides and at various distances? And what kind of numbers are we thinking about?
The idea is to send hundreds, if not thousands. We would probably send one every few days. The one reason is that we don't know a lot about interstellar space. We know there's dust. There's some evidence that we're in a local kind of, dust hole. I mean, there's not very much dust, particularly in the direction of Alpha Centauri. So the universe might have conspired in our favor. But even so, going at 20% the speed of light, this light sail will encounter dust. And now, fortunately, the dust would go right through and make a very small hole. But if it hit a vital component, it could destroy the spacecraft. We're trying to distribute across the sail and the electronic components, so they'll have some redundancy, but we expect that we'll lose a lot of them. So we would send hundreds. Now, where their primary purpose is to take images of the planets in the system, and of course they fly right by, and then they turn around and we'll send the data back. It'll take months for each image to get back. at the data rates that we can get. But it's hopefully within a few decades we'll get a lot better information of what that star system looks like. That it has, we already know there's 3 interesting planets in the Proxima system, potentially 1 orbiting Alpha Centauri A, and I suspect they're going to find a whole star system. So the idea would probably be to send a number of these to fly within a few million kilometers of each of the interesting planets. We hope that we can get a little more information than just images. We may be able to get a very simple spectrometer on some of these, depending on how the technology goes. But certainly the answer to the question is that we send a lot of them, first of all, because a lot of them won't make it. And we'll send a lot of them because we want to go to different locations in the star system. Proxima Centauri is about 10,000 astronomical units from the other 2 stars. So it's actually a different position. It's slightly closer than Alpha Centauri A and B. It's 4.2 light years rather than 4.3. So it's certainly an interesting system. We're interested in other star systems as well. We know there's planets orbiting the next nearest star, the Barnard star system. There are planets orbiting Epsilon Eridani and Tau Ceti. We're also, one of our other targets is 61 Cygni A and B solar type stars that are orbiting each other. And in that case, they have a several thousand-year orbit. So a variety of systems we would look at. Of course, they're farther away. If you want to get there in a few decades, you have to go faster. Our systems designer said, well, that's easy. You just make the array bigger. So rather than a few kilometers, it's 10 kilometers. But I think that these all look to be feasible in this century. I think that we can explore the solar neighborhood. And I think we're going to find from some other programs that we and others are doing that all of these stars have very interesting solar systems.
Mm-hmm. You mentioned that dust will blow a hole in components. Do we have any notion of how big a hole how much damage by volume it might do?
It's probably pretty small. I mean, it depends on the geometry, but at that speed, you just knock out a small chunk, maybe millimeters or at most centimeters.
Mm-hmm. Okay.
There are ideas that maybe we would we move the sail to be at right angles to the direction. Now that may be a disadvantage because then something would tear through the whole thing, long ways. But this is clearly something that we need to look at. Undoubtedly, what we would do, and in fact, we're looking at a potential prototype system you could build within a decade that could send things to near interstellar space and really tell us more about that environment. It wouldn't be going at 20% the speed of light, but maybe a few tenths of a percent. But that begins to get us out into real interstellar space. There's obviously interesting targets in the Kuiper Belt and Oort cloud. There are some people that believe that there may be brown dwarfs or rogue planets that are nearby. Hopefully we found one of those. Maybe it's only a few tenths of a light year away, and we can fly by those. So this isn't sort of a sort of Hail Mary in one project. This really is our expanding our scientific reach into the interstellar space, starting nearby.
Okay. An obvious question is how much will this project cost? But any estimate will surely turn out to be wildly inaccurate. So let me ask a more meaningful question. Say we have just finished sending a whole host of probes to Proxima Centauri. They're on their way, and all we have to do is sit back and wait for the data to come back to us. Having already built and paid for the array, at that point, how much additional money might it cost to launch similar probes to all 109 star systems that lie within 20 light years of Earth? An additional 10%, 5%, 1%?
It's a very interesting question. There's the cost of sending these is basically the power. And now that's probably it's quite a lot of power. So at current cost, it's probably a few million per probe, where the probe themselves only cost a few $100s. But clearly we can send hundreds or thousands. The challenge, of course, is if you built a laser array that was just sending things in the direction of Alpha Centauri, that's a lot cheaper than building one that can go in all directions. So it's probably a different photon engine that you would use to send things in all directions. That would have to be steerable and so forth. Now that's quite feasible. My guess is probably a steerable one may cost, within a factor of 2 of the initial one. Again, our target is somewhere between 5 and 10 billion for the array. So building sort of an all-directional one is probably, at least in our best estimate, is a few tens of billions. The interesting thing about that is that if it go in all directions, if the Earth was threatened by an asteroid impact, this is enough power to divert the asteroid. You basically, the asteroid is just hit like a light sail and you push it. So that's a real exciting possibility of having a something that not only sends probes to all these stars, but also protects us. And you could send much bigger probes to the outer solar system at very high speed. So there's probably a lot of value in building such an array. Now, one of the things, and Phil Lubin is certainly pioneered in some of this, is that, well, why put it on the Earth? He suggests in space, and it appears to me and a lot of others that the ideal place would be to build it on the far side of the moon. And then you don't have the atmosphere, then it's very easy to phase. The other reason to put it on the far side of the moon is, some people may worry that, oh, well, could be used as a weapon. It could, if it's on the Earth, it could blow up satellites, or if it's in space, it could be turned around. Now, I'm confident that we would control this with a global international regime that wouldn't make that happen. But if you had it on the far side of the moon, it can't be turned around. So I suspect that we may do the first one on the Earth that would be aimed just at Alpha Centauri. But then, if this is later in the century, I suspect our ability to manufacture these kind of things on the moon and put them there will be well within reach. So I can imagine near the end of the century or in the second half that we build a really big photon engine on the far side of the moon, and we use that for a lot of purposes. But it could it could send things to all the nearby stars, and that may even be the nucleus of James Cameron's starships. Although I believe in the second movie they turned out to be kind of evil, so hopefully humans will be better than they are.
Well, the rule in science fiction: something has to go wrong.
That's right.
Yeah. In addition to Breakthrough Starshot, Breakthrough Initiatives has also created other initiatives. For example, you're the chairman of the Breakthrough Prize Foundation. If you would tell us about the Breakthrough Prize, what is it, how it got started, and perhaps what is its future?
Well, the Breakthrough Prize is a very exciting effort, and it really was the initial part of our sponsor's idea. Mr. Milner he's a physicist by background, and about 15 years ago, he started to look at list of the most admired people on the planet. And those lists have, politicians, artists, entertainers, billionaires, scholars, and so forth. But there's very few scientists in those lists. You might find Einstein, and of course now maybe Hawking. And the point is that he and some of his colleagues realized that they've made literally trillions of dollars over the last decade or two based on scientific discoveries of a century ago. The electronics and quantum processes and atomic processes and so forth. And their concern was that who's going to make those discoveries now that are going to power our future and our development in the century ahead. So that being high net worth people, Mr. Milner and a few others like Mark Zuckerberg and Sergey Brin and Andrew Zwisky, and originally Jack Ma, and now we have a few other sponsors, have said, well, why don't we see what we can do to encourage people to kind of, if you will, make movie stars out of scientists. And, you know, being high net worth people, the first thing that came to their mind was, how about giving the world's largest prize? And then also having a ceremony that everybody wants to watch. You know, I don't know about you or the other viewers, but I don't think I've ever tuned into the Nobel Prize ceremony. You know, it's not one of those things that you got to watch. So they established the Breakthrough Prize. It's the largest prize in science. It's about $3 million US dollars, and there's 6 or 7 prizes in life sciences, mathematics, and physics, which is almost 3 times the size of that other prize I'm not supposed to mention very much. And, but it's the second thing was to have a ceremony that really would bring this home to the public. So the first year was the big ceremony was 2011. The sponsors wanted to have a kind of an Oscars of science, so they turned to the people that do the post-Oscar party, Vanity Fair, and I've never been to it, although I keep hinting I'd love to be invited. But they chose to have the ceremony in Silicon Valley, and the Vanity Fair and some other of the sponsors looked at where's the best place, and it turned out that NASA Ames, where I was the center director, has these really iconic 1930s airship hangars, which they thought would be really cool. So they asked if they could have the ceremony there, and I agreed, although I almost got fired for it. But one of the principles of if you have a big party is you always invite the landlord. So I was the landlord, so I got invited. But it's been there, except the last couple of years because of COVID, we haven't held it. This year we're holding it in April in Los Angeles. It's the first one outside Silicon Valley. But it's been very successful. The ceremony and the prizes have been broadcast live on Nat Geo and Discovery Channel and a few others. We also have sort of A-list entertainers that is the MC, and I mean, one of the first years we had Christina Aguilera sing, and it's kind of neat for me because I was kind of a co-host that I actually got to meet all these people, you know, and some of the presenters are people like, you know, Benedict Cumberbatch and others. So you know, it was again kind of a cool event. We've started a couple other prizes. One of them is the New Horizons Prize, which is not just for, you know, senior scientists, but for people early in their career in physics and mathematics, and that's a $100,000 prize. But probably to me the most fun one is about 6-7 years ago we started the Breakthrough Junior Challenge, and it's we ask young people between the age of 13 and 18 to do a couple-minute video on some science principle. The winner gets a $250,000 US scholarship wherever they want to go. The school gets a $150,000 laboratory. And to me, one of the coolest things is we give the teacher that inspired the student a $50,000 check. And I remember the first year we did it, we'd called the teacher, and the student hadn't told the teacher that he'd nominated him. And the teacher, at first, we had to convince him this wasn't some scam call from Nigeria or someplace, that we really did want to send him a $50,000 check. But it's been very good that we've had about 8 winners now. The majority of them actually are women. They're from a lot of different places around the world. We have a young lady that won from Peru, another one from the Philippines, a young lady from Mauritius, and other places, a young man from India. So it's been quite a exciting effort, and we hope to expand on this in the future, maybe regional prizes and so forth. But it's we get some 10,000 entries each year. I serve on the selection committee. I think nominally I'm the chair. It's really fun to listen to what these young people are doing.
Okay.
And so I think we're succeeding in inspiring the next generation.
And in case anyone's interested in getting their nephew or daughter or grandchild or whatever, where do they go to find out more about this, to sign up?
I would just, look, do a search on Breakthrough Junior Challenge, and it has the dates and what the entry criteria are. But Breakthrough Junior Challenge.
Okay.
And so it's really a neat program, and I really encourage young people to get involved in it.
Okay, excellent. Most people are familiar with the SETI program. Breakthrough Listen is also listening for alien signals. If you would describe the scope and scale of this operation.
Well, Breakthrough Listen was our first initiative. We announced it, as I said, in July 20th, 2015. And the idea is that we would spend $100 million over a decade or so to revitalize the search for a technosignature, evidence of a technological alien civilization. And it used to be called SETI, Search for Extraterrestrial Intelligence, but I think technosignature sounds a little better. This was really started, in the early 60s. The originator was Frank Drake, and Carl Sagan was an early proponent, and others, that could we use radio telescopes to find an alien signal. There was a lot of progress made. Of course, there was no repeatable signal. There was the famous WOW signal that was in the 70s that were found at the Ohio State University's radio telescope. But there was also a lot of controversy in the 70s. NASA started a modest program. It was actually based at NASA Ames. A U.S. senator gave it the Golden Fleece Award as being, and then a little later, a U.S. congressman caused such a fuss that it got canceled. After that, though, a number of private individuals picked it up. They founded the SETI Institute. Others at UC Berkeley did SETI at home, also privately funded. And so this had been moving along, but there was one effort that Paul Allen, the co-founder of Microsoft, funded to build a big radio telescope, the Allen Telescope Array. It was not going as well as originally thought, and then Paul Allen passed away a few years ago. But Yuri wanted to restart a lot of this effort, and so we based our program at UC Berkeley. The principal investigator is Andrew Simeon, Dr. Andrew Simeon. We now have collaborative time on most of the world's large radio telescopes, including the first part of the square kilometer array, which ultimately is a square kilometer in southern Africa. The first part of that is called Meerkat. It's 64 radio dishes. We've also worked with the Chinese 500-meter radio telescope, the U.S. Green Bank Radio Observatory. And the program has been expanded to use the Very Large Array in New Mexico, other radio telescopes around the world, most notably in Australia. The other part of the square kilometer array is a low frequency array called the Murchison Wide Field Array. But one of the telescopes that we had a lot of time on was the Parkes radio telescope. It's a 64-meter radio telescope. It's for a long time it was the largest radio telescope in the southern hemisphere. It was used to actually receive the Apollo 11 moonwalk signal. And if anybody hasn't seen it, there's a really lovely Australian movie called The Dish. And it starts out with people playing cricket in the radio dish. But I really commend it to everybody. But we've used that. I've also had a ride in the dish too, so it's kind of cool. But about 2 years ago, Dr. Simeon called me. It turned out it was on Halloween, and he said, I think we have a signal. And he said, it's interesting. It's from Proxima Centauri, which, we knew had an Earth-sized planet. And so I got very excited, and I opened a bottle of champagne. Before I could open the second bottle, he called back. He said, now, look, I want to caution you that this is most likely interference of some kind. He said, but it does have all the characteristics that we would expect. A very narrow band. It drifts in time, indicating that it's off the Earth somewhere. And it's not in a frequency band. I think it was around 900 and some megahertz that's used for a lot of other radio communications. So I put away the second bottle of champagne, and I said, now look, I don't want anybody to talk about this. We just need to do our homework. And he said, well, that'll take about a month or two. And so about 2 days later, there was a report in the Guardian that said that people had discovered this radio signal. So it was so much for secrecy. But in the end, we concluded that it was almost assuredly interference. There were a variety of reasons to conclude that. But it was interesting that we do have the sensitivity. That there was another tentative detection by the Chinese 500 meter, also ultimately concluded was interference. But I think we have the ability now to start searching for the first time over much of the sky. Our primary objective is to look at all the million nearest stars, and that takes us out to about 1,000 light years, and at least do a quick search to see if there's a beacon. So if there's something nearby, I think we'll find it. We've also tried to extend to different frequencies. We're looking at optical signals, potentially laser signals that would indicate laser communications. Increasingly, we're using lasers to communicate with, particularly in space. I might add that our Starshot laser is so bright that if you happen to be in the beam, you would see it at 5 billion light years. And so it's so if somebody's is aiming a Starshot at us, we'll see it.
Okay.
Long before probes get there. But
Okay.
it's a so this is pretty exciting stuff. Like I said, it's currently based at the University of California at Berkeley. We're moving the headquarters of it to the University of Oxford later this year. So both Berkeley and Oxford will be primary areas. And what we're really pleased with is that an area that was at one time regarded as sort of, pseudoscience is now being seriously considered. Increasing numbers of institutes and astronomers are really taking serious that we now have the capability to potentially find alien signals if they're there.
Okay. Breakthrough Message is another initiative. Describe that, if you would.
Well, initially we looked at if we did find a signal, what would you say back, or should you say it back? We talked about an initiative to kind of have a global effort to say, what would you say in this message? Although it turned out there was a lot of controversy about messaging, particularly from Professor Hawking. He was personally very much against it. So we decided to shelve that. We felt that probably the wisest thing is kind of what my father used to say. I guess it was Abraham Lincoln that originally said it. It said, better to be thought a fool than open one's mouth and remove all doubt. Let's listen before we talk. But the other thing is really to find, and we have another initiative called Breakthrough Watch, which I mentioned is there any evidence of life elsewhere? And we've looked at both things we could do inside our solar system and detecting some of these planets. But Breakthrough Message is, we felt that was best to kind of keep quiet for now. And we could certainly revisit that, but I think if we begin to see evidence of a real signal, then that would be something that should be reopened. But there's huge philosophical, ethical, and even security issues about, do you answer?
Mm-hmm. You were a key early innovator and proponent in the area of small satellites. For example, the Clementine mission, for which you received the NASA Outstanding Leadership Medal. If you would talk about the Clementine mission to the moon a little bit.
Well, that was a really fun mission. You know, I've been a space nut since I was a little kid. And the first books that my mother got me to read one was called Planets and the other was called Stars. I have to be honest, I like the Stars one better because it had a picture of aliens or something in the end of it. Said that we don't know of any aliens in our solar system, but there might be some around nearby stars. But you know, I grew up during Apollo. You know, when I went to the University of Michigan in 1967, everybody wanted to be an astronomer or involved in space or an astronaut or both. There were 120 people that were going to major in astronomy at the University of Michigan in my introductory astronomy class for majors. End of it, 6 of us got a degree in astronomy. I think a lot of people understood that, well, you had to really learn calculus, which wasn't as easy as everybody thought. But the 2 of us got PhDs, and I think I'm the only one still doing astronomy, but in a matter of speaking. But I had the strong interest throughout my career that really beyond Earth orbit was very important, and particularly the moon as a start. I was working at the National Space Council at the White House in 1989 to 1992. I was actually the staff officer for the first President Bush's Moon Mars Initiative. And I and another staffer were bemoaning the fact that NASA didn't seem very eager to do anything and kept giving us, you know, hundreds of $billion projects. And we had both worked in the missile defense program, the so-called Star Wars program. And we were aware that a program there was developing interceptors called Brilliant Pebbles. And literally on a napkin in a bar, we sketched out said, well, we could modify one of these things to go to the moon. It also appeared, it occurred to us that we were having a lot of problems with the ABM treaty, that if you tested one of these things in Earth orbit, you know, it potentially violated the ABM treaty. But it turned out the lawyers told us, well, if we tested it around the moon, it didn't. And I'm not sure whether they were right or wrong, but we used that excuse. So we did the Clementine mission. It was very exciting. We used the technology being developed by the Defense Department. And in I think it was 1993 that the mission was launched. It had the trials of or the perils of Pauline sort of in the way. We orbited the entire moon, got the first set of images, you know, full images, multicolor images of the moon. A lot of interesting stuff from that. NASA in the end did work with us very closely, and they set up the science team. One of the initial interesting discoveries was that we used the transmitter on the spacecraft as it orbited the moon to bounce off the permanently shadowed craters in the pole of the moon and actually receive the signal that was the first indication that there might be ice in the bottom of those craters. Later confirmed, by the way, by a mission we had at NASA Ames, the L-Cross mission. But it was kind of a very cool mission. We were going to go intercept an asteroid, but we had a software glitch, and the spacecraft was appropriately named as Clementine. It was lost and gone forever. But great success. I think the total cost of the mission was about $80 million.
Mm-hmm. I followed it pretty closely myself. I was very excited about the idea that there could be water, frozen water on the south pole of the moon. And so when it gave the result, high probability, it was very exciting for me. Yeah.
Well, and it does appear to be pretty real. So I think it's going to enable us to to live for long periods of time on the moon, and if I can use the word, a lot of people don't like settle, but I think humans will live on the moon in the next few decades and permanently.
Mm-hmm. You've been a big proponent of robotic and more recently crewed space missions to near-Earth objects. What do you view as the importance of these objects and the benefits that they can provide to us?
Well, I've always been excited about asteroids, and there's sort of three reasons that asteroids are interesting. The first one is we wouldn't be here if it wasn't for the asteroid 65 million years ago that wiped out our competitors, the dinosaurs. And they are threats. And I was a military guy, so it's very, I think, significant that I think Carl Sagan said it best. He said, if the dinosaurs had had a space program, they would still be with us, or we probably would never be here. So they've always been exciting to me for that aspect. Second, they are very interesting scientifically. They are the primordial building blocks of the solar system. But third, they are readily accessible from a energetic standpoint, and I'm really convinced that the asteroids represent the key to large-scale industrialization and exploration of the solar system because of their resources. And indeed, when I was at Ames, we persuaded the Grand Duchy of Luxembourg to invest heavily in asteroid and lunar mining. That's one reason I'm here. I'm an advisor to the Luxembourg Space Agency on space resources. But I think that maybe the third one is most important. Clearly, the moon is also a source of resources, but ultimately, when you look at SpaceX's plans to settle Mars, the fuel, I think, is going to come from asteroid gas stations and potentially the moon as well. That they're really the resources we need. Initially, of course, I think the key one is volatiles, water and other hydrocarbons. But ultimately, metals and so forth. It's probably overworked, but even a small metal asteroid has hundreds of trillions of dollars worth of platinum group metals. Probably a lot easier to get at than in order to get platinum group metals. Currently, we have to go ever deeper into the crust, and as hard as it is to get around in space and do things, it's easier than going a few kilometers down in the crust. So I think that asteroids are very exciting. So I've always been very interested in. And when I worked at NASA as the center director, there was a lot of controversy: was it Moon or Mars? And the leadership at NASA really said, well, asteroids may make a easier place to go first. From a energetic standpoint, it's actually easier to go to an asteroid than it is the lunar surface. So there was the asteroid redirect mission that was in NASA's plans, and I know they've changed them now, but I hope they go back to doing something with asteroids.
Mm-hmm. Some people may have a misunderstanding of asteroids. We tend to think of them as mostly between Mars and Jupiter, but they are all over the solar system. Can you give a picture, a description, a little bit of how many are available for easy access that come nearer the Earth and stuff?
Well, clearly, as you noted, that the majority of asteroids that we see are in the main asteroid belt. There are additional asteroid belts, between the outer planets. There's clearly a large quantity in the Kuiper belt beyond Pluto. In fact, Pluto itself is probably an asteroid in some sense, a big one. Dwarf planet, I guess, is the official term. Because of the interactions with particularly Jupiter and the main asteroid belt, a lot of these end up being scattered, if you will, into the inner solar system. Meaning that if they had an interaction with Jupiter, their orbits are bent, and then with interacting with some of the inner planets, they can have even circular orbits over time. I think there's, if I remember the number, that over a kilometer, there's many thousands. You know, and over 100 meters, there's probably 100,000, you know, maybe even 1 million. You know, so that at any given time, there's probably a small asteroid that's a few tens of meters between the Earth and the Moon. Some of these are in very accessible orbits. As I said, the energetics of getting to an asteroid, even though it may be farther away, is a lot less than going to the surface of the Moon. So it's, you know, we know of thousands of these, but, you know, they're of things that might be of interesting size, there's probably millions. So it's a huge resource that we can use. It's also, of course, a potential threat. I mean, that these things hit, you know, the big ones, like the one that killed the dinosaurs, is like 10 kilometers in diameter. But there are many that are tens or hundreds of meters in diameter that could do a lot of damage. So not only should we look at them as a positive resource, we should look at them as a potential threat. And the first and most important thing is map where they all are, especially the bigger ones.
After becoming NASA Ames Research Center Director, you actively developed Ames' capability for rapid prototyping of small spacecraft. What did you see as the benefits of this?
Well, there's a number of things. I mean, probably the first thing is the cost and technology. My chief engineer then, who's still my chief engineer, used to hold up his cell phone and he'd say, you know, this does everything a satellite does. And this thing cost a few $100s, and the satellites that we have today is, you know, or then were, you know, metric tons and cost, you know, hundreds of millions. So he asked, you know, why can't we use this technology to do a lot more in space? And of course, you know, in the late 90s, the CubeSat idea, but those originally were just regarded as a way to teach people about satellites. But I had a group of people at Ames that listened to his talks and said, well, you know, why can't we actually make a satellite with a phone? And so we started a project called the PhoneSat project. And it turned out the people that did that have now started a number of companies. You know, probably the best known one is Planet. But they actually launched 3 satellites that used a phone. And they were some of the first satellites launched from the International Space Station. President Obama visited Ames a couple of times, and I always tried to get him to, you know, he would bound off the plane and he'd say, you know, hi, we're really proud of what you guys are doing at NASA, and then he'd walk on. I figured, well, if I could actually get him to come and visit, you know, it'd really be cool. So about the second or third time he came there, instead of saying, welcome to NASA Ames, Mr. President, I said, welcome to NASA Ames, Mr. President. We have just launched the world's cheapest satellites. And so he stopped for a moment. I said, oh, I got him. And he said, how cheap were they? And I said, well, Mr. President, there were 2 of them that were 4,000 and 1 of them were 10,000. And this showed why he was a really good politician. He looked at me and says, we're giving you guys too much money. and I remember the administrator asked me a day or two later, he said, you look like you were talking to the president for a while on the, you know, when I saw the clip, and he said, what did he say to you? And I said, oh, he said, we're doing a great job. I didn't have a heart until later to tell him, he said about the, you know, we're giving you guys too much money.
Yeah.
But you know, that was, there were others also working on it, but that CubeSats could do incredible things and are doing incredible things. I think now the exciting thing is even going smaller, like the ChipSats, the Graham class. The other thing is that beginning to use networks of satellites, of CubeSats. So it's, in some sense, I think that many of the key things, maybe most, we don't need big satellites. And it's, so that was kind of my belief of, you know, it turned out I had, you know, in the science area at NASA there, you know, there were the big science centers, which were JPL and Goddard. And in fact, I'll probably get in trouble for saying this, but I used to criticize JPL, and I said JPL stood for Just Pay Lockheed. I mean, they've done wonderful things. Don't get me wrong, but it was very hard to win a competition against those big centers. So we kind of end random to say, well, we can just do small ones that nobody cares about. Of course, they eventually decided they would do CubeSats too, but it's I really credit my team at Ames of changing the paradigm. And a lot of people in the new space industry went through Ames and were inspired by it. And I think it's the mainstay of new space is to build CubeSats, and now they're beginning to go into cislunar space and interplanetary space.
Okay. I've got several more questions, but we're running a little bit low on time. Let me see. Yeah, let me ask you this one. You served as a scientific co-investigator for 3 NASA space science missions, most recently IRIS, IRIS, the Interface Region Imaging Spectrograph, launched in 2013, to study the sun. Tell us about IRIS.
Well, IRIS was that was the one time we won.
Okay.
NASA has a small Explorer program, and we'd tried many times and we didn't win. But so we teamed with Lockheed's Advanced Technology Center, and a good friend and an old mentor of mine was Alan Teitel, and he was a big advocate of doing things low cost. And the really exciting physics on the sun is sort of above the visible surface, above the photosphere. It's sort of what heats the corona and what's called the chromosphere, which is the region where you get all the flares and other activities. And the key thing by going to space and by having especially shortwave detectors and doing images, we could begin to really map that physics. You could see how the magnetic fields are working at very, very small scales. And this was called, it's the interface region between the corona and the photosphere. So the IRIS mission was designed to be the first one to really probe that very exciting area. We had some major discoveries about the physics of how the solar atmosphere works. And it was launched on the Pegasus. It was one of the last launches. But it went very well. Now at the time there was a lot of sort of seat of the pants things, but we managed to get it on budget, on schedule, and I'm really proud of that mission. My job was mostly going over and terrorizing the Lockheed leadership that they really needed to let the purchase orders go through. It was an exciting program.
Okay. Yeah, I do need to wind up. Let me ask you, what makes you feel hopeful about the future of space exploration, both inside our solar system and beyond it? And also, what worries you about the future of space exploration?
The future of humanity requires that we expand into the solar system and eventually interstellar. In fact, this was Stephen Hawking's key thing, that there's lots of bad things that can happen in our solar system. And there's a lot of bad things that can happen on our planet. I mean, they are happening. So that, I think on the positive side, I think the technology is coming along. We, within at most a few centuries, will have the ability to go interstellar, and within a few decades, interplanetary and expand human presence. What worries me is actually the bad part of that is, horrible things that could happen on the planet. We have conflicts now that are the closest to nuclear war that have been since any time in my lifetime. And I lived through the Cold War. So those are serious setbacks. Going wrong, they could be permanent setbacks. So that's what worries me.
Okay. And final question. Since you're a sponsor of the IRG Symposium this summer, the goals of the IRG must be very important to you. And which of the goals and what of the goals stand out most important in your mind?
Well, I don't know. It's I have to say that the first thing is really to figure out where we want to go in the nearby star systems and how we're going to get that data. Hopefully we can find a potentially habitable and, obviously if we find a life-bearing planet, that is really exciting, but it also raises issues of, if it's already occupied. But I to me, I've always found the most exciting part is the destination. Mm-hmm. So I think that, obviously the propulsion capabilities are important. But ultimately it's the destination.
Okay. Well, thank you, Doctor, for taking the time for the interview. It was great stuff.
Well, thank you, and hope to see everybody at the conference.
That was Dr. Pete Worden. This has been From Here to the Stars, a video series produced by the Interstellar Research Group. The IRG is a non-profit organization dedicated to thoroughly exploring the science and engineering that can eventually open up the reality of interstellar travel. Find out more about our next symposium at irg.space. I have been your host, Stephen Euin Cobb. If you enjoyed this video, please hit the like button, and you can subscribe to our channel for other such videos. On behalf of all of us here at the Interstellar Research Group, I thank you.